Welcome to our discussion on rational functions. As always, you can fast forward to the section that you need to look at in more depth. Let's start with the definition of a rational function. It is simply just any function that is a combination of two polynomial functions, right? A polynomial function divided by another polynomial function, where of course the bottom polynomial function can't be the zero polynomial, which basically just means it can't be zero, right? Because we can never have zero in the bottom of a fraction, which also means that the bottom function, whenever it's equal to zero, we have to take that out of the domain. So the domain of our function is always going to start off with all real numbers, and then we're going to take away any numbers that make the bottom equal to zero. Here are some examples. So you really don't care about the top, it's all about what's happening down here. So our first function is everything except, the domain is everything except for 1. This one is very simply everything except for 2, except for the fact that the top also does factor out, right? And then we'll see that in a second. And then this one you would have to factor it to x minus 4 times x minus 2, and then it would be everything except for 4 and 2, right? So your domain would be everything except for those two numbers. Now that's this one. Let's go back to this example C, where I mentioned that the top and bottom have the same thing in it, right? This would factor to x minus 2 times x plus 2 on top, and you have the x minus 2 on the bottom, and these do in fact cancel algebraically, and this function is algebraically equivalent to just x plus 2, which means it's going to graph as a straight line. But that's just an algebraic equivalence. The original function is still this function. So when you graph it, yes, you have a straight line. Yes, it has a slope of 1, and yes, it has an intercept of 2, right? So it looks something like that. But the original function still has this discontinuity, this problem at x equals 2. So technically, when you're over here at 2, there will be a hole in your function right there. So it'll be a straight line with a hole in it. So just keep that in mind, that even if the functions reduce algebraically, and you always want to reduce them if you can because it helps you with graphing and things like that, the original function is still the one that you have to consider when you're figuring out the domain. Okay, so those two things are algebraically equivalent, but the original function is still the one that tells you what the domain is. Defining vertical and horizontal asymptotes. Well, vertical asymptotes is just wherever the function is undefined. So it's those ideas that we saw before at 2, and the other one was at 4, and things like that. Here's some pictures. Right, the blue lines are your asymptotes, and it just means that as x gets really close to that number, the function gets asymptotically close, right? That just means it nuzzles up right next to it, but doesn't actually ever touch it, because you can't actually plug that number into the function. That value a is something that makes the function undefined. That is where you had division by 0 happening. Some other examples, right? You can have where the function goes to positive infinity on both sides of the line, negative infinity on both sides of the line, or it can go either direction, right? Down on one side, up on the other, and vice versa. The only way to figure that out is to just try some test points. If a happens to be 2, then take 1.9 and plug it into your function and just ask yourself, is the answer going to be a positive number or a negative number? You really don't care so much about what it is. You don't have to worry about plugging 1.9 into a function and dealing with decimals and all that stuff. It's really just, is the function going to be positive or is the function going to be negative? Because then that'll tell you if it's going to trend down towards negative infinity or up towards positive infinity, depending on if you're getting positive or negative numbers, right? Horizontal asymptotes are completely different. Horizontal asymptotes are the value that the function, the height of the function approaches at the extremes. So we're looking at what happens to the function way out at the edges. You could have a function that's doing all sorts of weird stuff here in the middle, right? More smooth maybe. But as it keeps going out, it tends to level off. And then that would be your horizontal asymptote, even if it does something on this side. Or you could have a function that does it in the other direction, does something weird and then levels off. And then this ends up being your horizontal asymptote. Finding verticals and horizontals, if they exist, right, if they have any, because not every function has them. Well, we already saw that to find your vertical asymptotes, it's all about looking when the bottom is equal to 0. So we go back to our definition of what a rational function is, and you're just concerned with when is this thing equal to 0. Back to these examples, we can see that in the first one, x equals 1 makes the bottom 0, so x equals 1 is going to be a vertical asymptote. And if you were to graph this function, you would have a vertical asymptote over here, right, at x equals 1. And then the function itself is going to do something on each side of it. Well, if you take a number just slightly bigger than 1, so 1.1, you can see 1.1 minus 1 is positive. So when we're on the slightly bigger than 1 side, it's going to go up to positive infinity. Take something slightly less than 1, 0.9, 0.9 minus 1 gives you negative, it's going to go negative on that side. And then you can do some more testing to figure out what happens in the other directions, but for right now we're just going to concern ourselves with what happens at the vertical asymptotes. The next example, we would have to factor it out and see that we get it at plus and minus 3, and then again we could test on each side of both of those. And then the last example doesn't have any zeros because x squared plus 1 can never equal 0, right? I mean, if you did the algebra, you end up getting x squared plus 1 equals 0, which means x squared equals minus 1 when you move the 1 over. And this is impossible, at least in the real numbers, right? We would have to use imaginary numbers. The idea of a rational function whose graph has a hole, well, that goes back to the one that we saw earlier where the top and bottom canceled, right? So we've already talked about this. You factor out everything, see if they have anything in common. You divide out those common terms, and then you graph what's left, right? This function is now algebraically equivalent to just x plus 3, which is a simple straight line. However, there is that hole in it because the original function still had this problem of x minus 3 being in the bottom, which means you cannot let x equal 3. So you still have to have that problem, right? When x equals 3, there's a discontinuity. And by the way, it doesn't have to be a straight line. This same theory, the same idea works for anything. You could start with two polynomial functions of much higher degree, and when you cancel things out, all of a sudden you're left with just a quadratic, and you're you're graphing a parabola somehow. But the original function had a problem at 5, right? Then you would just have a hole here. Or maybe the original function had a problem at 5 and at 0, right? Then you'd have 2 holes. It just depends on what the original function was. So when you reduce, it doesn't always have to reduce to a straight line. This idea of a graph with a hole and it having to be a straight line is not true. It can algebraically reduce to anything, and then that new reduction could still have holes in it because of the original function. Here's a second example that of course is going to go back to a straight line. Well, actually it's not a straight line, right, because it's 1 over x minus 2. So here is an example of exactly what I was talking about, where we have a different function, a non-straight line function, and there is our hole in the graph at -2. Horizontal asymptotes, we talked about them before. How do we find them? What are the rules? They're very simple. It's all about the powers, right, the degrees of the two polynomials. So everything boils down to the leading term, top and bottom. That's all we're going to concern ourselves with, and that's going to tell us if we have a horizontal asymptote, and if so, what kind of horizontal asymptote it is. Here are the simple rules. Let's remind ourselves of what n and m are, right? N is the degree of the top, m is the degree of the bottom. So if the degree of the top, n, right, is less than the degree of the bottom, so the degree of the bottom is bigger, then you always have a horizontal asymptote at y equals 0. But this comes back to, you might ask yourself why, and it comes back to the idea of rules of polynomials. If we have a polynomial function, f of x, and it equals 3x to the fifth plus 2x cubed minus 7x squared plus 100, let's say. What does this function look like, right? What is it approximately equal to as x gets really big in either the positive or negative direction, right? So as x goes to positive infinity or negative infinity, this function really becomes equivalent to just 3x to the fifth. All of these smaller pieces don't matter. Remember, we did the whole thing where you factor out the highest power, so you factor out an x to the fifth, and you're left with times 3 plus 2 over x squared minus 7 over x cubed plus 100 over x to the fifth. And now as x gets really big, all of those things with x's in the bottom all go to 0, and so this function ends up looking like just 3x to the fifth. Okay, well, what if our original function was now a rational function, and on the bottom we had a 5x to the sixth plus 4x squared plus 1,000, who cares? Again, as x gets really big in either direction, the bottom is going to just look like 5x to the sixth. So this rational function is really just going to look like this fraction, which simplifies quite easily to just 3 over 5x, right? X to the fifth and x to the sixth reduced down to this. And then now ask yourself, okay, what happens to this function as x gets super big in either direction? It equals 0. So that's why whenever the bottom has a higher degree, right? This was m and this was n, so m was bigger. Then by the rules of polynomial functions, as x gets really, really big, it's just all about the leading terms, which reduce down to this, and we get a higher power of x on the bottom, which means the whole thing goes to 0, and that's why we have a horizontal asymptote at y equals 0, which of course is the x-axis. If the two degrees are equal, then you can see from this same example, if these were now both 6's, then this becomes a 6, right? This means that both x's are still here, which means it now reduces to just 3/5, right? Because both x's cancel. And so now we get that it levels off at a y equals 3/5, the a over b. Now this last rule is true, that if the top is bigger than the bottom, we don't have a horizontal asymptote. But there is one special case where if the top is exactly 1 degree bigger than the bottom. So let's look at an example like something simple, 3x to the fourth plus 2x plus 5 all over, how about 2x cubed minus 10x plus 7. We know that as we go out to infinity or negative infinity, it's basically going to be 3x to the fourth over 2x cubed, which of course reduces to 3x over 2, right, or 3 halves x. 3 halves x. Well, 3 halves x is just a straight line, right? That's mx plus b, where b is 0. So that's a straight line at a slope of 3 halves. So what that means is whatever the function does in the middle, when it gets out here to large values, it's going to have a slant asymptote of 3 halves, and the function is going to shoot off to positive infinity at that angle. Same thing over here in the negative. It does whatever it does, and then at a certain point it goes down to negative infinity at roughly that slope as well. So you can see there is no horizontal asymptote, but there are what are called slant or oblique asymptotes because the function will tend off at a certain straight line angle. Finding horizontal asymptotes, very simple. You just follow those rules we discussed. You look at the degree at the top, you look at the degree at the bottom, and then decide what's going on. So with our first example, the degree of the top is 1, right, because this is a linear one, and the degree of the bottom is also 1, so they're equal. So we're looking at the leading terms, right, leading coefficient, and that's why it's negative 5/3, right, because this leading coefficient is actually a negative 3. If we were to write the bottom in proper form, it would be negative 3x plus 1. So you see how you get that negative 3 as your leading coefficient. The next one, B, we have the top has a degree 1, the bottom has a degree of 2, so the bottom is bigger, so we know that it's going to level off at y equals 0. The third example, we have the top is 2, the bottom is 1, so according to the book, we have no horizontal asymptote, but in this case, since it's exactly 1 degree bigger, we do have that oblique asymptote. If it's 2 or more degrees bigger, you have nothing, right? Think about the example of make this a 4 all of a sudden. So now it's 3 degrees, right, bigger, right? It's degree 4 versus degree 1. Now look what happens. This goes to 3x to the fourth over x, which reduces to 3x cubed, and that thing just explodes, right, for big values up to positive infinity at a huge rate and really fast down to negative infinity in the negative direction. So it doesn't even have slant asymptotes. It has nothing. So you only get the slant or the oblique asymptotes when the top is bigger by exactly 1 degree. And if it's bigger by 2 or more, you just get nothing. But all of those can be lumped into the same category of no horizontal asymptotes. Graphing rational functions, well, just like graphing any other function, you're going to do the same thing as far as find intercepts, find some test points, and graph what you got. The only difference is with rational functions, you also have to worry about asymptotes. So the first thing you want to do, find intercepts just like normal. Find your x-intercepts, find your y-intercepts, and it's no different than any other function. To find your x-intercepts, you set the function equal to 0 and solve, and to find y-intercepts, you set x equal to 0 and solve. The nice thing about rational functions is no matter how ugly they get, if you set this thing equal to 0 and try and solve, i.e., right, you're trying to find your x-intercepts, well, in order for a fraction to equal 0, doesn't that mean the top of the fraction has to equal 0? So you basically just ignore the bottom, and it's all about taking that, setting it equal to 0, doing what you got to do, right? Factor out, factor with linear terms, whatever you have to do for whatever's left. If it was a linear function, you know how easy that is. It's quadratic, so we treat it like a quadratic. If it was a cubic, you would have to use tools for factoring a cubic, and so on and so forth, and you find your x-intercepts. Simple, just like normal. Y-intercept, also just like normal. You're plugging in 0, only now you do have to worry about the bottom because you're plugging 0 into the entire function. So you get your y-intercept, also fairly simple. Next, find the vertical asymptotes if they exist, and that's where you set the bottom equal to 0, right? So we set the top equal to 0 to find the zeros of the function. We set the bottom equal to 0 to find those asymptotes. So there's our asymptotes at plus and minus 3. Again, when you set it equal to 0, you use the same techniques that we used before, depending on what the function is. In this case, it's a quadratic. Determine if it has any horizontal asymptotes using our rules. So the top function had a degree of 2. Right? The bottom function has a degree of 2 as well. So they're equal, right? And when they're equal, the rule is look at the leading coefficients. The top one had a leading coefficient of 2. The bottom one had a leading coefficient of 1. That's leading, not leasing. Of course, this coefficient is not trying to lease a car. And then 2 over 1 is just 2. Next, you can test for symmetry, and that means plug in the negative x and see if you get the same value for x which in this case you do, so you know it's symmetrical around the y-axis. Um, Testing for symmetry is fine. It does help, but really once you've done the first three steps and you have asymptotes and intercepts, you can really just start using test points to get you the overall shape of the graph. So you don't have to worry about testing for symmetry. Testing for symmetry can help save you some time, but it's not really necessary. Locate the graph relative to the horizontal asymptote. So that idea is just figuring out, does it level off above or below it? And now start plotting those points, right? You've got your intercepts, plot those, then do some test points. So you plot all of your asymptotes, then you plot any intercepts that you had discovered. In this case, you discovered this one, and they didn't put it on the graph, but those two there. And then here's where they're showing symmetry. If you would have discovered that it was symmetrical, that would have helped. But if not, just use some test points, right? You're looking at this and go, okay, between 0 and -3, I'm going to look at -1 and -2 and plot those. +1, +2, plot those. Because it's just a simple, just do this. This is what I always do when I have to sketch a graph. X's and Y's, man. Just plug them into the function. When x equals -1, what does y equal? And then connect the dots. When x equals -2, what does y equal? Plot the dot, right? +1, +2. Then I'd go out here in this range, right? Because you got to go on the outside of the plus and minus 3. So try -4, +4, -5, +5, and plot a bunch of dots and connect the dots. It's just that simple. You don't have to worry about making it fancier or more complicated than it is. Here they're just walking you through the same idea with another function. Since the top is greater than 0, there are no x-intercepts, right? It never equals 0. You set x equal to 0 to find the y-intercept of -1. You set the bottom equal to 0, and there's your vertical asymptotes. It's not multiplied out, but the degree of the bottom, of course, is a 2, right? Because you'll get an x squared. In fact, if you multiply it out, you're going to get x squared, blah, 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 blah. So now I have my leading term. Degrees are the same, 1 and 1, so now I know my horizontal, right, is at y equals 1, which is what they said there. There is no symmetry. The zeros of the denominator are where you get your asymptotes. So here's our figure. They're plotting basically the asymptotes and the intercepts. And then you check each quadrant for what's happening with your function. So in between -2 and 1, you use some test points and you see that it's always negative. Between -2 and beyond, it's always positive. And it helps you get an idea of the general shape of the curve. And there it is. But again, rather than doing test points to figure out if it's positive or negative, I would just do x, y, and plot some points, right? First things first is you always want to graph your asymptotes, because that gives you the quadrants that you're concerned with. And then you always want to plot your intercepts. So the only intercept we had was 0, -1. Now once that's done, go back and start using some test points. Plug in -1, see what you get. Plug in +2, +3, +4, right? -3, -4, etc., etc. Because it's pretty easy to plug those numbers into this simple function and get results. Sketching the graph of this. So another example. I'll just go through these kind of fast, and you can pause if you want to really look at the steps, but it's the same thing. Find your intercepts, find your asymptotes. I wouldn't bother with symmetry, just plug in some points, right? Use some test points. We only had the horizontal because there were no vertical. Then I would use a bunch of test points and go from there. Obviously symmetry would help a lot with this one, but it's not a necessary tool to have in your toolbox. Graphing rational functions with oblique asymptotes. They're finally going to talk about these. So as we know, an oblique happens whenever the bottom is exactly 1 degree smaller than the top, right? The top has to be exactly 1 degree bigger than the bottom. Then you get an oblique. Some simple examples. Here's one where you've got an x squared over an x, so degree of the top is 2, degree of the bottom is 1. That gives us an oblique. If you do the actual polynomial division, that's fine, but you can also just ask what happens when x goes to 0. I don't like what the book is doing here. This is confusing. Why do I need to do division? I can just look at what happens to this function as x gets really, really big. It basically becomes x squared over x, which equals x. So I know the oblique is going to be at the line y equals x, right? 45-degree angle. This is going back to that idea of test points. You've got your vertical asymptote at -1, what's happening on each side of it. I would just say go ahead and plot your asymptotes. So there's your vertical asymptote, there's your horizontal asymptote, and then plot some points to see how it matches up. Finally, an example in business, a revenue curve. So here's our function for a revenue curve. Find and interpret those various numbers, sketch the graph, and then use a graphing calculator to estimate the tax rate that yields the maximum revenue. We see x here, of course, is our tax rate. So what does it mean r of 10? Well, doesn't that mean that x is equal to 10? And since x is the tax rate in percent, then isn't that the revenue in billions of dollars when our tax rate is 10%? And wouldn't the next one be the revenue we get in billions of dollars if our tax rate is 20, and so on and so on and so forth? And if you plug them in, these are the numbers you get. If you graph it, either by hand or with technology, it looks something like this. And then from the calculator graph of this, you can use the trace feature to see that the tax rate of about 23% produces the maximum tax revenue. And what that is you would have to use the trace feature, and it starts moving along the graph, and then it outputs the y values. And as you move along here, as x changes, you'll get bigger and bigger y values, and then all of a sudden they'll get smaller, and in between there you'll find the maximum. Actually, if you have a fancy calculator, you can actually have it find the maximum value for you specifically, but it is right around 23%. And that's it, guys. That's everything you need to know about rational functions.